Okay, so our plan for today is to finish up a last problem or two in 3.3 on mixture applications and to work through 3.4 solving geometry applications. Uh, and jump this bit down there. Here we go. Our quote of the day today is don't walk over dollars to pick up pennies, or there are many kind of variations uh, of this quotation. I don't think it's one of those that, anybody famous has said. It's just like kind of, one of those things that's said. And the idea is that, we all have limited time, energy, effort, cognition, whatever it may be to spend. And we want to focus on the higher yield things, right? If we're walking over dollars, if we're ignoring higher benefit items to pick up pennies to hyper optimize, say, lower yield, lower benefit areas, that might not always be the right decision. So, that could look literally like, for instance, spending a bunch of time shopping sales or something to like, save 30% on a can of beans or something like that, and spending so much time on those kind of things, hyper optimizing that when you're shopping for a car or something that's a $20,000 purchase, you don't have the time to devote to that, right? I'd rather pay double for a couple of grocery items because the absolute scale is smaller. But if I even overpay by 1 or 2% on a $20,000 car, that's $200, $400, right? So uh, we want to spend our time optimizing the most the things that are the highest yield. And what does that maybe look like in your coursework as a student? We can look at this, I think, a couple of different levels. One level, say, looking within a class. Well, for instance, this class, we have some homeworks, we have exams. The exams are weighted more heavily than each individual homework set. And if it's great to do the homework. Don't misinterpret what I'm saying here. But if there's a problem that's just really bugging you on a homework set, and we're coming up to an exam, if you can get 100% on this one homework set versus 97% on that homework set by doing this one problem, but that problem takes you 45 minutes or an hour to work out for whatever reason, maybe it's just a more complicated problem, or maybe it's a bonus problem, something like that. Is that a good time spent that week when maybe that drops your exam grade 5 percentage points because there was a topic you didn't quite get to review? Now, don't get me wrong. Like I said, if you should do the homework, you should even do the problems that you're struggling with. You should actually, that's where the most learning occurs. So that's definitely beneficial. But if you've got an exam coming up, you have to weigh the yield. Can I just let this problem go and make sure that I'm really solid for the exam? That might be the best choice in that scenario. We've all got limited time to spend that we have to divide up, or even between courses, right? Every faculty member likes to believe that their course is the only course that you're taking, and that you're, or at the very least that our course is the most important course that you're taking. But I think we have to be realistic and accept the fact that that's not always true. In fact, a lot of times that's not true. And so when you're dividing your time or your attention or your effort between your coursework, maybe this just isn't the semester where you can get an A across the board in every course. If you have to decide, I'm going to put more effort into this course to make sure that I'm really solid on that grade, and that means I take a bit of time away from this course, and I might take, a letter grade lower. That might be a trade-off that has to be made, right? But make that trade-off thoughtfully. Which of this coursework is most important for you moving forward? Or if you're in danger of failing a course, that might be one that, if you're in danger of failing, but you're currently passing, that might be one to put a little bit more effort in just to bolster that grade and make sure that you don't fail it and have to retake it, right? So I think this is a good thing to kind of keep in mind. And I think related to this is an idea that the psychiatrist Carl Jung, back kind of in the days of Freud and Jung. So Jung was like early 1900s or so. Freud maybe a little more like late 1800s, early 1900s. So I don't think this is a statement that Jung ever actually wrote. he wrote in German, obviously, so he didn't write this statement, but I don't think this is even a direct translation of anything from Jung. But I think this idea, is maybe a paraphrasing of a good bit of his body of work. And that's this idea, that which we need the most, we found where we least want to look, right? We tend to enjoy working on things that are our strengths because those come naturally to us. We find those easy. And when we do them and we see that we're excelling at them, that makes us feel good. But it's usually our weaknesses we need to work on. So I think this is, where are you likely to find the dollars? Probably in the areas that you're, that you're avoiding. And this is certainly true for me. We would much rather hyper optimize our pennies. We would much rather spend our time working on our strengths because that makes us feel a lot better. But sometimes a little bit of that really gritty work, working on some of the more challenging stuff, is where the highest yield is. Same thing in coursework, right? If there's a section or a topic that you really struggled with, and 4 other sections in that chapter that you felt pretty good on, it's much nicer to study the stuff that you feel good on because you're like, yeah, I'm doing great, and you shouldn't ignore that. That's important to keep that motivation up, but don't ignore that one section that you don't understand as well, or that you struggle with. Um, when that pops up on the exam or something, that's not going to be the best feeling to know, ah, man, I should have studied that, right? So, all right, so those are the ideas for today. So any questions before we move into, or before we continue, mixture applications? All right, so I put this question on screen last time, and I asked you to think through it a little bit. And I actually mentioned that even though this seems like a very different context than the finance question, it's actually a pretty similar question to that one. So let's take a look at this one. So here we have a scenario where we have access to 2 different types of vinegar. One is cooking vinegar, which is 5% acid by volume, and the other is cleaning vinegar, which is 7% acid by volume. I have a couple surrounding questions here. This bold one is really the kind of crux of the 3 questions. It's the most challenging, and it's the one that really the math comes up the most in. But the surrounding 2 questions, I think, are helpful to maybe help us to get a better gut feeling, to get a better understanding of what's going on here. So let's actually start with the 3rd question here. So when we say that vinegar is, or this cooking vinegar is, say, 5% acid by volume, what we mean is essentially that it's 5% vinegar and 95% water is really what we mean by that, roughly speaking. 100% vinegar, 100% acetic acid is very nasty stuff to work with. We're not, going to work with that anywhere outside of a chemistry lab, so it has to be diluted pretty significantly. So we might ask ourselves then, is there a way that without using some kind of crazy chemistry or something like that, can we just combine these 2 solutions to make a solution that is, say, maybe 8% acid by volume, if that's what we desire? We want a stronger acidity. Maybe we want a stronger cleaning solution. We would like it to be 8% acid by volume. Can we combine these 2 to make that happen? I think we can kind of see that the answer is no, right? I mean, if any combination between 5% acid and 7% acid is going to be between 5 and 7% acidity. If I started with a bit of my 7% acid and started adding in the 5% acidity cooking vinegar, that 7% is just going to get a little more diluted and start working its way to a lower and lower acidity, or vice versa. The 5% will work its way up a little bit, but the 5% will never get brought above 7% by adding a 7% acid, or vice versa. So no, we can't combine the 2 to make an 8% acid by volume. We also can't combine the 2 to make a 3% acid by volume. Now, thinking outside the box a little bit, is there a way that we could easily, without using crazy chemistry or anything like that, make a 3% acid by volume if that's what we desired? Maybe this cooking vinegar is a little too acidic for what we need. And basically, yes, if we think outside the box a little bit, we can add some water to the 5% acid by volume. We essentially have access to what you might call 0% acidity vinegar, just tap water. I mean, tap water has minerals and stuff in it, so maybe I'm making the chemists annoyed by saying something like this, but but we can, reduce the acidity by maybe adding water from the tap, or if we really wanted to, maybe distilled water or something like that, but we can't easily increase the acidity. Most folks don't have glacial acetic acid sitting around the house, so uh, you know, by mixing these two together, the best we could do is to get an acidity between 5 and 7%. Okay, and another interesting question here. This might seem kind of silly. You're saying, why would a grocery store or Walmart or somewhere like that stock two different types of vinegar at 5% and 7% acidities? I mean, we're calling one cooking vinegar and one cleaning vinegar, uh, and it doesn't have to do necessarily with the purity or the food safety of it or anything like that. Although I mean, in practice it might, but why are we calling 5% acidity cooking vinegar that you might eat and 7% cleaning vinegar, which we kind of have a feeling is more, uh, I think caustic is the wrong word. I think caustic means basic, but you know, uh, less fun to deal with, right? Something you probably wouldn't want to put in your mouth. So if we look at this, we might say, well, there's only a 2% difference between these two acids, between these two vinegars. Uh, why are we harping on this difference? We'll be a little bit careful. So this is a little aside, but I think it is an important aside to understand just in general context, and particularly in finance things, when somebody says, "Oh, they're increasing the tax rate but from 22% to 24% or something on this, whatever it is," you say, "Oh, that's just a 2% increase." But does that mean that every $100 in taxes you were paying, you're going to pay $102 in taxes now? Well, not really. So we have two different ideas. There's percentage point increase, and here that is 2%. So what we would say is we'd say something like there's a 2 percentage point increase. But what's the percent increase? And actually, I think it was last class, maybe the class before, we talked about percent increase. And remember, that is new minus old. Well, new minus old is what gives us our percentage point increase, 7 minus 5. So increasing from 5% acidity to 7% acidity, but then divided by old. And it's really this divided by old that is the difference between percentage point increase, which is just the numerator, versus percent increase. Or in other words, I have a 7% minus 5% over 5%. Or that is 0.02 over 0.05, or that's 2/5, or that's actually a 40% increase. So the 7% acid, the cleaning vinegar is actually 40% more acidic than the cooking vinegar. It's a 2 percentage point jump, which doesn't seem big, except for the fact that it's on the scale of very low numbers to start with. A small increase on the basis of a small scale can be a pretty significant percent increase. So there actually is a pretty significant difference between these two concentrations, between how these two the cooking vinegar versus the cleaning vinegar might act in a solution or something like that. So don't look at your cleaning vinegar and say, oh, it said to use 5% vinegar, but this is 7%. That's not too far away. I don't know how safe that is to use or whatever, but I probably wouldn't do it. It's actually 40% more acidic. Okay, so the mixture question, the algebra question that we want to answer now is, okay, I have these two different types of vinegar. How much of each should I combine to make 30 fluid ounces of a solution that is 6.2% acidic? Can I achieve 6.2% acidity? Yes, I can, because it's between 5 and 7%. So I can, start with some amount of 5% acid, kind of add some 7% acidity vinegar to that, and that'll slowly raise the acidity. It'll increase the volume and also raise the acidity until I get up to 6.2%, right? I could raise the acidity as high as 7% by putting essentially no 5% acid in and then adding 7% to it. All right. So again, this is a pretty challenging problem because just the context is so abstract, right? We're talking about acids and we're talking about percent acidity of a solution and all of that. So that's why I wanted to take just a few minutes here and kind of get our bearings. Okay, so how much of each vinegar should be combined? Let's make the number of fluid ounces of cooking vinegar, cooking or 5% vinegar that we're going to use in our solution, and B, the number of fluid ounces of cleaning, or 7% vinegar. Now we get one equation pretty easily, right? We have two variables. We're searching for two equations. One of these comes about pretty easily. We need a total of 30 fluid ounces. So A plus B equals 30. That's one equation. That's our easy one to get. The more challenging equation is this one. I want this solution to have 6.2% acidity. If you look back in your notes to last time, we'll see some inspiration for how to approach this. If I have A fluid ounces of cooking vinegar, then the amount of acetic acid that I have, or this would be kind of like if I have an interest rate of 5% over a certain time on a certain amount, then the dollars in interest that I have, that's kind of the analogy here. The amount of pure vinegar that I have in the solution is going to be 5% times A. That's the amount of fluid ounces of pure acetic acid that I have in this mixture from the contribution from A. And then I have 7% of the amount of cleaning vinegar, B. So 0.07 times B is the amount of acetic acid, the amount of pure vinegar that I have in this solution from the contribution of the cleaning vinegar. So this is the total amount of acetic acid in the solution when I mix A fluid ounces of cooking vinegar with B fluid ounces of cleaning vinegar. What's the total amount of acetic acid I want in the full solution? I want 6.2%, but we can't just stop here. I need to multiply by the amount, by 30 fluid ounces for the full solution. I want my 30 fluid ounces at 6.2% acidity. That's going to give me, that product is going to give me the amount of acetic acid in my solution. So again, we've kind of worked up to this problem. We did our kind of more basic financial problem. We did a more complex financial problem. And then we have this problem where the math actually looks very similar to that more complex financial problem, but the scenario is different. Okay, so what do I have here then? I have A plus B equals 30. I can solve that for one variable in terms of the other. Maybe I'll make B 30 minus a. And then I can take my more complicated equation. Maybe the first thing that I will do here before I substitute in b is multiply by 100 to bump these decimal points over to the right too. So I have 0.05a, that term gets hit by 100, bumps this decimal point 2 to the right, making 5a. Same with the 0.07b term, plus 7b. My 0.062 term has the decimal point bumped 2 to the right, so it becomes 6.2 times 30, or that's 62 times 3. 6.2 times 30 is 6.2 times 10 times 3, and I'll use that 10 to move that decimal point one more place. So I've cleared all of my decimals. And now I will take my b equals 30 minus a, swap it in there. And what's 62 times 3? Well, that's 60 times 3 plus 2 times 3. I think that's 180 plus 6. Okay, so let's take our left-hand side and distribute. I end up with 5a minus 7a, that's negative 2a, plus 7 times 30 is 210, equals 186. I can add 2a to both sides, subtract 186. That's an a on the right side, believe it or not. 2a, there we go. 210 minus 186, 186 to 200 is 14, and then 10 more is 24. So A has to be 12 fluid ounces. So we need 12 fluid ounces of the cooking vinegar. And then, of course, B is 30 minus A. I need the rest of the 30 fluid ounces has to be cleaning vinegar. So B is going to be 30 minus 12 is 18 fluid ounces of cleaning vinegar. These are the two amounts of cooking and cleaning vinegar that I would mix together to get a solution that is both 6.2% acidity with a final volume of 30 fluid ounces. So if I need 30 fluid ounces for some reason, I don't have any waste and I don't come up short. So I have the right volume at the right acidity this way. Okay, so before we wrap up section 3 and move on to geometry problems, let's do one last exercise. This exercise, I think, is going to be a little bit less challenging than maybe this one or the previous financial one because it's a little less abstract, but it's going to have a similar feeling still. So, so take a look at this exercise. Maybe take about 5 minutes on this one. Be careful, read through the problem, figure out what you're looking for, take your time setting things up, or even, thinking through a couple of scenarios. What if I had, what if I had all cashews in my mix? What would that look like? Why wouldn't that be a good answer? What if I had all peanuts in my mix? Are there desired mixes, desired costs that I cannot achieve? What are the range of costs that I can achieve by mixing peanuts and cashews, right? So ask yourself some of these kind of similar questions as up here to really get a handle on the context, the gut feeling for the problem, and then try to work through the algebra, come up with, there's going to be two variables, and you're going to want to come up with two equations, and then work through solving them. So a good bit of work to do on this problem. Let's plan to take about 5, maybe even 6 minutes working through this exercise as kind of our capstone for this section. Okay, it's about 5 minutes in, so I want to touch base and then maybe give you another minute or two, but just to make sure that we've all kind of made it to this point. So I'm reading through here and I see peanuts sell for $5 a pound, cashews for $8 a pound. How many pounds of cashews should be mixed with 14 pounds of peanuts to obtain a mixture that has a value of $5.90 per pound? Now, if we were reading not too carefully, we might really be tempted to just do something like P plus C equals 14. But we see that's not really what's going on here, right? Actually, we're told the amount of one of the ingredients in the mixture that we have. So if we call P the number of pounds of peanuts and C the number of pounds of cashews, well, P is 14. So, we might think of, we want to make a full batch that would be however much peanuts and cashews, but we are almost out of peanuts. So we're going to use the last bit of peanuts, the last 14 pounds, and how many pounds of cashews should I mix with that is really the question here. So I know that P is 14. So that's, believe it or not, one of my equations. P equals 14. It's a nice, very simple equation. How do I get the second equation? This is the more complicated one. The cost for the overall mixture costs $5.90 per pound. And how much does the overall mixture weigh? P plus C. Let's just keep P as P right now and not swap in 14. We could have, in theory, gotten a more complicated equation up here instead of something simple like P equals 14. But just so we can see all that's going on, oh, and I actually did jump the gun on the right side here a little bit. Let me fix that. P goes there. So $5.90 per pound for the whole mixture. That's the cost for the mixture of peanuts and cashews, times, well, what's the weight of the peanuts and cashews? P plus C pounds. I notice on the left, my pounds go away. My per pound multiplied by a number of pounds gives me, well, those divide out and it just gives me dollars left over. So this left-hand side is denominated in dollars. On the right-hand side, what is the contribution of the cost from each of the two components? Well, I have $5 per pound times P pounds. The peanuts are $5 per pound. Again, my pounds divide out, and I'm left with just the amount of dollars in value from the peanuts that are in the mixture. And similarly with the cashews, this term, the $8 per pound times C pounds, represents the number of dollars of value that are in the mixture from the contribution of the cashews to the mixture. So cleaning this up a little bit, I see everything is in dollars. I will not write my dollars everywhere now. So I have 5.90 times P plus C equals 5P plus 8C. So once things are cleaned up a bit, that is my that is my second equation. Now take another minute or probably another minute or so to solve this. So I'll set another minute or so on the timer and we'll come back and discuss the answer in a minute. All right, let's wrap up this question and section 3 on mixture applications. So I choose to multiply both sides by 10, being careful that I have 1, 2, 3 terms to multiply by. Don't forget any of those. So the 5.90, 5.9 times 10 gives me 59 times P plus C. And on the right side, I have 50P plus 80C, making sure to distribute my 10 appropriately. If you needed to write out another step there with parentheses on each side and do that carefully, definitely go ahead and do that. I remember that my equation up here, my other equation, which was quite simple in this example, is just P equals 14. So I'll substitute in P equals 14, and I get 59 times 14 plus C equals 50 times 14 plus 80C. I will distribute my 59 over here, and I switch the order just to make them look a little nicer. And this is what I get. This is my equation in standard form. I'm actually not going to do the multiplications 59 times 14 and 50 times 14 because they'll work out pretty nicely in just a minute here. But I see I have a linear equation in standard form. Number times C plus number on both sides. Let me get my variable terms together. I think I want to subtract 59C from both sides. So on the left, I have 59 times 14. On the right, I have 50 times 14. And then 80 minus 59 is plus 21C. I want to isolate my variable term now by subtracting 50 times 14 from both sides. And if I have, so on the right side, they go away. If I, on the left side, have 59 amounts of 14 minus 50 amounts of 14, I'm just left with 9 amounts of 14. The same way, if I had 59p minus 50p, I'd have 9p, right? I have now isolated my variable term, and I'll isolate my variable itself by dividing both sides by 21. I'll get C equals 9 times 14 over 21. Well, 9 is 3 times 3, and 14 is 7 times 2. Well, this 7 times 3 makes a 21 that can divide that out. So I think C equals 6. How many pounds of cashew should we mix with 14 pounds of peanuts? 6 pounds of cashews. And as a kind of side note, this proportion tells us what proportion between peanuts and cashews we need for a mixture of $5.90 per pound. We always need a 14 to 6 ratio or a 7 to 3 ratio. 7 pounds of peanuts for every 3 pounds of cashews, or 7 ounces of peanuts for 3 ounces of cashews, whatever it may be. We need a 7 to 3 ratio, or 70% peanuts, 30% cashews, to make our mix cost $5.90 per pound. So if I even abstract a little bit further away from this problem and realize that actually, if I'm interested in targeting a certain cost per pound, or for that matter, a certain acidity, or for that matter, a certain interest rate, right? All 3 of these problems were fairly similar in the mathematics behind them. The answer that I get actually also indicates a proportion where if I invest my money in this proportion between fund A and B, or I mix my chemicals in this proportion between cooking and cleaning vinegar, or if I mix my nuts in this proportion of peanuts and cashews, then I'll end up with this rate in the mixture, either this number of dollars per pound for cost, or this interest rate for the financial problem, or this percent acidity for the cleaning solution or vinegar solution problem, right? So a ratio of 14:6 or 7:3 or 7 out of 7 plus 3, 7/10, 70% peanuts, 30% cashews, scale it up or down to create whatever volume I want will get me a mixture of $5.90 per pound. A mixture of 12 parts to 18 parts, or 12 out of 30, or what's that? Well, I can divide out of 6. That gives me 2 out of 5, or 40%. If I mix 40%, what was this cooking, right? It was A. Yeah, 40% cooking vinegar with 60% cleaning vinegar, that will get me a solution that is 6.2% acidity. And then I can scale that 40%, 60% ratio up or down as needed to make whatever volume I want. So abstracting away a little bit more, generalizing a little bit further, we actually see that we even get even more out of these answers than we might have at first seen. We get an idea, a sense of proportionality that we can scale up or down if in another scenario we wanted a different volume. Now, if we wanted a different percent acidity, or if we wanted a different cost, then we would have to reevaluate our proportionality. We would have to reevaluate what our mixture looks like. But we could kind of scale things up and down proportionately in order to maintain the same cost or the same percent acidity or the same interest rate. So what we've done here is actually even more than what we might have realized that we had done if we hadn't taken a minute to step back and really look at things and ask, what all can I glean from this answer? Any questions on any of this? Okay, let's jump into our next section then. Section 3.4, solving geometry applications. Okay, so a few reminders on some topics. This is prerequisite material, so if any of this doesn't really look familiar, or you're not super comfortable with it, go back and review the material. That's kind of a natural part of really any coursework. Is in just about any course, you're going to come up against a few things that are prerequisite material that that you don't feel super comfortable with. You know, it's taking the time to go back and fill in those knowledge gaps. That's something that everybody has to do, no matter how well prepared you are in every class. So, you know, if you're looking at some of this and saying, wait, I don't remember that, go back, pull up a Khan Academy module, or look earlier in our book, or even go back to the OpenStax pre-algebra book, the one that we use for MAT090, and go to whatever section and drill a few problems, review that topic. Okay, so triangles. When we're talking about geometry here, we're talking about plane geometry, two-dimensional geometry, and one of our most famous shape, the triangle, of course. The triangle is so named because it's triangle. It has 3 angles and 3 sides for that matter. And let's call these angles A, B, and C. Let me zoom this in a little bit. And with angles A, B, and C, we have a sum of angles formula that A plus B plus C has to be 180 degrees. We can essentially take this as a definition. This is derived from some more basic geometry principles, but we'll basically just take it as a definition that the sum of the angles in a triangle is 180 degrees. A right triangle is a triangle where one of its angles is 90 degrees. And we signify that one of the angles is exactly 90 degrees, usually by putting a little kind of square box in that corner. Now, of course, a triangle, if it has 3 angles, none of the angles can be negative. So all the angles have to be non-negative, but not just that. we can't even have an angle being 0 degrees, right? If I imagine a triangle with angle 0 degrees, if I keep shrinking, oh, OneNote's trying to outsmart me. Unfortunately, it's succeeding. I don't know what that says about me, but if I keep shrinking this angle, we see that eventually when we get to 0 degrees, we actually just collapse to like a straight line. It's not really a triangle anymore. So we actually need our angles to be strictly greater than 0 degrees. But that means if I tried to make a triangle with two right angles, maybe A is 90 degrees and B is 90 degrees. Well, now I've used up all of the 180 degrees. C would have to be 0. So a right triangle is where we have exactly one angle is 90 degrees. We cannot have more than one 90-degree angle in a triangle. So in a right triangle, we can talk confidently about the 90-degree angle or the side opposite the 90-degree angle. And there's no ambiguity there. There can only be, at most, one 90-degree angle in a triangle. The Pythagorean theorem makes a statement about right triangles. So suppose that I have a right triangle, and suppose that I have sides of length A and B. I'll call these A and B sides. Sometimes they're called legs. And they're the they're the edges that are adjacent to the 90-degree angle. And then suppose that I have a side C that is the one that is opposite the 90-degree angle. As an aside, C will always be the biggest side. C gets a special name. C is called the hypotenuse. So it is the one that's opposite the 90-degree angle. And these sides A and B, I think I mentioned but didn't write, we often call them legs. So the legs of the right triangle versus its hypotenuse. And the Pythagorean theorem says that a squared plus b squared equals c squared. So I think my favorite proof of the Pythagorean theorem, I'll sketch it here. I'm not going to go through all of the details. But you basically start with a with a square, and we have a right triangle that has legs A and B, and we copy that 4 times. So we construct a square in some sense using these triangles, and I'm not doing a great job with the keeping the proportions the same, but I use 4 copies of a right triangle with legs A and B. So this is triangle 1, 2, 3, and 4. And that leaves in the middle another square. And if we're using this triangle over here, we'll say that that square has side lengths C. And what I can actually do is kind of slide this triangle, say, that way, because these two sides are parallel to one another. And then I can kind of slide this triangle up here. And I end up, or oh, I went the wrong direction. I can slide this triangle down here and this triangle over there. And I end up with my 1, 2, 3, 4 triangles represented plus 2 squares. So on one hand, the empty space that's in the bigger square that's not covered by the triangles is c squared, this middle square here. And in the other case, I'll be able to see that my 4 triangles, 1, 2, 3, and 4 cover a certain portion of this bigger square, but leave empty b squared and a squared. So I can see that the empty space that's not covered by the triangles is simultaneously c squared as well as a squared plus b squared. Again, I didn't go through all the details of the proof here. This is a pretty famous proof. It's probably, if you look up Pythagorean theorem on Wikipedia, it's probably like the first proof that's there. It's very visual, very easy to understand. But so that's just kind of, showing you an argument that you can make to prove Pythagorean theorem. So lots and lots and lots of proofs of Pythagorean theorem are out there, but I think that's the easiest one to remember, that if you build this square with these 4 triangles like this, you can kind of shift them around and make this interior square that's c squared, or kind of 2 squares that are a squared and b squared areas. Okay. So next up, the idea is a perimeter and area. So let's start with a triangle, not necessarily a right triangle. So say I have a triangle that has sides of lengths A, B, and C. The perimeter, well, what the perimeter is really saying is take one of the points of intersection, one of the angles, let's say this one here, between A and C, and choose a direction, clockwise or counterclockwise, doesn't much matter. We'll start going this way. And in some sense, just kind of like walk around the shape until you get back to where you started. How far have you gone? So the perimeter in this case, to go from here up to this point, would require going A units of distance, then another B, and then C to get back to where we started. So the perimeter is, let me get rid of this star over here. The perimeter is the sum of the lengths of the sides of the figure. A plus B plus C. And then let's say for a certain triangle, we have a base width. I just realized that I called these sides A, B, and C, and I want to use B for base, but maybe I'll use capital B to represent base. And a height of the triangle. So suppose that my triangle has a width, what I'll call base, capital B, and a height H. So the area is 1/2 times the base times the height. The easy way to remember this area formula is by looking at the special case of the right triangle. Here, my height H is just one of the legs, and my base B is the other leg length. And I see if I put 2 of these same triangle together, kind of glue them together this way along their hypotenuses, I actually end up with a rectangle that's width B and height H, and I know the area of a rectangle is B times H. So 2 areas of a right triangle give me pretty clearly area B times H. So the area is 1/2 B times H. Now, be careful, this isn't a proof. I didn't just prove that the area of all triangles work this way. But really, this is kind of the crux of the argument. And this is just more of a memory device. The crux of the actual argument, or the actual argument, looks kind of like this. I have some triangle that's maybe not a right triangle. I cut it in half with a vertical to make 2 90-degree triangles, and then I can make a copy of this one. I can make a copy of this one. And I can basically do what I did here with right triangles, just do it twice on the two sides of this vertical that I dropped here. Again, I'm going pretty quickly through this material because this is prerequisite material, so this should look very familiar. This should be kind of a dusting off the cobwebs thing. If you're really not following at all, either pop in office hours. I'll 10:30 to 11 today, and 9 to 11 tomorrow, or send me an email or look back through the prerequisite material in the book. And rectangles, I cheated a little bit, I guess. I already kind of used the area of a rectangle a couple of times in my digressions over on the right side, but for rectangles, we have one set of parallel sides that has a certain distance and another set of parallel sides that has a potentially different distance, and they meet at 4 right angles. So that's a rectangle. 2 sets of parallel sides that meet at right angles. If I just said 2 sets of parallel sides, I could have something like this, a parallelogram. So I have 2 sets of parallel sides, also with the constraint they meet at right angles. And my perimeter, I actually think this is a little bit of a tricky perimeter because it's almost so simple. We want to just jump to the answer, and we might be tempted to say something like L plus W because it kind of looks like the area formula, but we actually have to be careful. There's 2L plus 2W. Or we could write it as 2 times L plus W. So just be, at least in my mind, half the time I'm almost like tempted to make the perimeter L plus W because having these extra 2's floating around, just seems a bit strange, but make sure to include those 2's there. And my area is length times width. Okay. Let's look at a couple examples. So first example, the measures of 2 angles of a triangle are these numbers, 107 degrees and 32 degrees. Find the measure of the third angle in degrees. So let's try to draw this. 107 degrees, I know that's bigger than 90 degrees. If I had a right angle, that would be 90 degrees. So this triangle is going to have an angle that's what we call an obtuse angle, 107 degrees. The other angle given, 32 degrees, is an acute angle, 32 degrees, and find the measure of the third angle in degrees. Maybe we'll call this C. So I know that 107 degrees plus 32 degrees plus C in degrees. Well, those 3 added together have to give me all 180 degrees of the triangle. Well, hey, this is just actually a really simple linear equation to solve. I have 139 degrees plus C equals 180 degrees, or C is just 180 degrees minus 139 degrees. C is 41 degrees for the measure of the third angle. So I have my obtuse angle and then 2 acute angles to go with it. If I ever have an obtuse angle, it can be the only obtuse angle. I can't have 2 angles that are above 90 degrees for the same reason I can't have 2 angles that are equal to 90 degrees. I could have a triangle with 3 acute angles though, like for instance, 60, 60, and 60 degrees, an equilateral triangle. So, okay, what about this example? Consider a right triangle. So let's not skip over that. We have one 90-degree angle. with one leg having length 12 and the hypotenuse having length 13, compute the length of the other leg. So let me draw a schematic. Now, one important thing to remember is that in geometry, uh, just because the picture looks a certain way doesn't guarantee that the measurements will be that way, right? If I have, if I draw a triangle where one leg is visually exactly twice that of the other leg, so this is like a 2-to-1 ratio visually, at least I tried to make it that. This might be 6 and this might be, 1. So this is a schematic representation, not meant to be necessarily perfectly proportionate and perfectly well proportioned. We try to make it kind of reasonably so that like legs that measure longer look longer, but the accuracy of the schematic representation is not really what we're going for here. All right, so we have a right triangle. I did put my 90-degree angle there. One leg has length 12, the hypotenuse is 13. Well, we know which one's the hypotenuse. That's the one that's opposite the 90-degree angle. Let's write that in. That hypotenuse has length 13. One of the legs has length 12. I guess I'll label this one 12 because then it, that looks about the same length as the 13 one. And then we want to compute the length of the other leg. Let's give that a name. Let's say A, for instance. Well, my Pythagorean theorem has something to say about this relationship. It says that A squared plus 12 squared equals 13 squared. Now, a little side note, you might be looking at this saying, wait, this is an unfair thing to ask of me. We haven't talked about quadratic equations yet. That's later on in the course. This is a very simple quadratic equation. In other words, we can basically treat this like x plus 12 squared equals 13 squared and then solve for x, right? X would be 169, which is 13 squared, minus 144, which is 12 squared, or x is 25. Right? Or in other words, we see that really just we have a squared equals 25, and this is a trivial equation to solve, right? This isn't something that we need some big understanding of quadratic equations to solve or factoring or anything like that. What number squared gives me 25? A has to be 5. So that's my answer. So as far as this section is concerned, any kind of, quote, quadratic equation that would come up in this section at this point would be able to be solved this way. And then we can either solve this by inspection, or let me rearrange my windows here and show you on the calculator how to do this. Give me just a second to get things arranged here. There we go. So if I have a squared equals 25, we say that a equals the square root of 25. I'm being a little flippant here with some of my details because we haven't gotten to quadratic equations yet, but this would really be one of two potential solutions for a. But this is the solution that we care about in these cases. So we're leaving some of the more nuanced material for when we do talk about quadratic equations a bit later. But here a equals square root of 25. And if I look at, if I type in 4 and then say diagonally up from the 7, we see there's a little x superscript 2, x squared button. 4 squared gives me 16. If I do second, this yellow button up here, that's kind of like the shift. It like gives you, it allows you to use all of these yellow operators. Most of these are things that, we don't really know what they do, but you might see like pi over here above the caret operator as like a shift caret. But if I do second x squared, that puts in a little square root icon. And if I do square root of 25, that gives me 5. I mean, this one I could figure out, but if I needed to do square root of, 17 or something like that and wanted an approximate answer, I might ask the calculator for help on that one. I see 14.1 or so. So if I need to use the calculator, I can. But again, the algebra on these is going to be straightforward. So you won't have to do any really complicated quadratic equations work. The algebra will be simple enough, and maybe at the end when you get number squared equals number, or sorry, variable squared equals number, to solve, for a problem here or there, you might have to type it in the calculator, but for the most part, they will be ones that you can even just kind of guess the solution and get it correct. Any questions so far? Okay, let's look at these next two. All right, so we have two exercises here. Sorry. Both of these exercises are, again, pretty straightforward, especially relative to the length and complexity of the Section 3 mixture applications that we had recently done. So won't take too much time for these, maybe take about 3.5 minutes for both exercises. So we'll come back in about 3.5 minutes, and as usual, I'll jot down some notes as we're going along. So take about 3.5 minutes, work through these two, and then we'll come back and discuss the answer. Okay, it's about 3.5 minutes or so. So let's talk about these two answers. So we draw out our schematic. We have a triangle has sides 7 feet and 8 feet and a total perimeter of 21 feet. So I'll label two of the sides 7 and 8 and give the third side a name. We'll call it C. So on one hand, I know my perimeter has to be 7 plus 8 plus C, measured in feet, of course. And on the other hand, from the information in the problem, my perimeter has to be 21 feet. So 7 plus 8 plus C has to be 21. 15 plus C equals 21 means C equals 6. And all of these are in feet. So if I have feet minus feet minus feet, I get a unit of feet. So everything's in nice consistent units, so we didn't have to do any conversions, anything like that. Being a good math guy, I try to avoid unit work as much as possible. So, so there you go, 6 feet. Second exercise is a little more challenging. Consider a right triangle. So we have a triangle with one 90-degree angle where both legs, well, where both of the sides that are adjacent to that 90-degree angle have equal length of 3. So it is important that we get the 3's in the right place. If I put a 3 here and a C there, that wouldn't be correct. So my right triangle has legs that are adjacent to the 90-degree angle, and it has a hypotenuse that is opposite the 90-degree angle. It's the side that where neither of its edges or corners touches the 90-degree angle. Well, Pythagorean theorem says that 3 squared plus 3 squared equals c squared. The thing by itself, the c squared by itself, is the hypotenuse. Well, I just have two lots of the same thing, or 2 times 3 squared equals c squared. I see that 2 times 3 squared is 9 times 2 is 18. So c squared equals 18, or c equals square root of 18. And we plug that in the calculator. That's about 4.2. One little interesting thing that we see from this exercise is that if I need to go over a bit and then up a bit, if I was like standing here and I had one path that goes like this, I would have to walk 3 plus 3, or 2 times 3, or 6 feet, or whatever units of distance. If I were to go along that path, the kind of horizontal and vertical path. On the other hand, if I were to cut kind of straight across the field, I would be going, well, I wrote over here, square root of 2 times 3. Oops. Square root of 2 times 3. That's the just cutting straight across. Or that's about 1.4 times 3. 1.4 is 70% of 2. So it's about 30% shorter to kind of cut directly across than it is to go vertically and horizontally. Something really interesting, I think. What if instead of cutting straight across, what if I went over a little bit, then up a little bit, then over a little bit, then up a little bit? That feels closer to going diagonally, right? It feels like following this path. Maybe I'll color it in red so you can see it a little better. It feels like following this path is a little closer to going diagonally. I'm just kind of like zigzagging around a diagonal, kind of in a sense. It feels like this should be a little more efficient. Maybe a little less than 2 times 3, but still a little more than 1.4 times 3. Or if I went, over a tiny bit, up a tiny bit, over, up, a whole bunch of times, I mean, I'm doing a pretty horrible job of drawing it accurately here. Maybe my little person is drunk, but you get, so if I go over and up, if I like go left, go like 1 step and go turn right and go 1 step and keep zigzagging like that, I mean, I'm basically just tracking right along this diagonal. That should be like pretty close to 1.4 times 3, it feels like. I think one of the strangest paradoxes in math is how far have I gone horizontally? Gone this plus that. I've gone 3 units horizontally, and I've gone 3 units vertically. This is still exactly 3 plus 3 or 6 units. Even this one, I go a little bit horizontally, a little more, a little more. The horizontals all add up to 3, and the verticals, if you believe that any of these are actually vertical, also add up to 3. Actually, no matter if I'm only going horizontal and vertical, no matter how many times I switch from going horizontal to vertical to horizontal to vertical, no matter how close I make this jagged line look to the actual straight, kind of cutting the corner line, it'll always be exactly 6 units long. It's only when we switch from, from the horizontal vertical mentality to actually going at the angle that we abruptly go from 6 units of distance travel to, what was it, 4.2 units of distance traveled. I think that's a really interesting thing. It kind of feels like if I can save 30% of my distance or effort by cutting the corner directly, if I kind of cut the corner a little bit by going kind of horizontal and then vertical and horizontal and then vertical and kind of hugging that red line up here a little more closely, it feels like I should be able to get a little closer to, my 30% savings, or I should get some savings out of that, but I actually get 0 savings out of this or that strategy. It's not until I get to here until I actually point myself in that direction and just go straight there, that I actually get the savings. I don't know if there's like some kind of hidden life lesson in there or something. I don't know. Like, maybe not. Like, unless you completely change your thinking, you don't get the benefits or something. I don't know. But anyway, I think that's a little interesting little side note on this. Okay. Um, any questions on any of this so far? Okay, let's take a look at this problem. The area of a rectangle is 256 square feet. The width is 32 feet. What is the length? Okay, so we're dealing with a rectangle. Let's get a schematic drawn. Oh, that's a bit of a wonky rectangle. There we go. If I really want to make it obvious that it's a rectangle, I'll maybe put in my right angles, but usually this is very clear from the context of the problem that what I've drawn here is a rectangle. So I'm not going to write all of those in. It just kind of clutters everything up. The width is 32 feet. So one of these measurements, we'll call it the left-right measurement, is 32 feet. And the length, let's give it the name L. That's what we don't know what it is. We're going to call it L. And the area, on one hand, has to be the length times the width, or 32L. And on the other hand, from the problem, it's given as 256. We might be looking at this and we might get a little confused with the units, but remember that 32 is in units of feet. And my length is going to be measured in units of feet as well. Feet times feet does indeed give me square feet. So areas are in square feet for that reason. I have kind of one measurement, say like roughly speaking, a horizontal measurement that's in feet and also a vertical measurement that's in feet. And somehow the product of those gives me an area. So my areas are in square feet. That does make sense. Okay, so my area is 256 square feet, and that's going to be 32L. So 32L equals 256. Well, this isn't too bad. I just divide both sides by 32. And both 256 and 32 are powers of 2. But we can just start chipping away at it. So 256 is 128 times 2. 32 is 16 times 2. And those 2's divide out. 128 is 64 times 2, and 16 is 8 times 2. Those 2's divide out. And now I might recognize, oh, 64 is 8 times 8. So 64 over 8 is 8. So my length has to be 8. And again, that's coming in with a unit of feet. My length has to be 8 feet. Width 32 feet, length 8 feet gives me a rectangle with 256 square feet as the area. Any questions so far? Okay, let's take a look at this exercise. So maybe take about, let's just take about 2 minutes to do this one. This should be a pretty quick exercise. Read through it carefully, draw a schematic, come up with an equation, and get the answer. Maybe about 2 minutes or so. Should be a pretty quick one. Okay, let's take a look at this one. So here we have a rectangle. We're told something about how the width relates to the length, and we're told the overall perimeter. We want to find the dimensions of the rectangle. We want to find the width and the length of the rectangle. So we draw a rectangle. We have a width and a length that we write on the rectangle. And on one hand, we know that the width is 2 meters less than the length. The width is L minus 2. On the other hand, the perimeter of the rectangle, which we know is 2W plus 2L, we know that that measures to 58.3 meters. And maybe I should have put meters down here on these answers. So my perimeter 2W plus 2L equals 58.3. And I have this first equation, W equals L minus 2, that I'll pop into that perimeter equation for W. So I have 2 times parentheses L minus 2 plus 2L equals 58.3. And working through that, I have 4L equals 62.3, or L equals 62.3 over 4. I could either put this in the calculator, or I could realize that 62.3 is 60 plus 2 plus 0.3 all over 4, or 60 over 4 is 15. 2 over 4 is 1/2, or we'll call that 0.5. And 0.3 over 4 is 0.15 over 2, or I think that's 0.075. And if I add these 3 decimals together, I get 15.575 as my length. My length is 15.575 meters. And then pretty simple to get the width from there. The width is simply 2 meters less than the length, 13.575, which my 3 there looks really messy, but 13.575 for my width, both of course in meters. Any questions on that one? Okay, let's look at this next example. I don't know if we might have time to get to the exercise, I'm not sure. Okay, next example. Brian borrowed an 18-foot extension ladder to use when he paints his house. If he sets the base of the ladder 6 feet from the house, how many feet of the side of the house will the top of the ladder reach? So let's take a look at this. We can draw maybe like a little picture first, and then turn that into a schematic diagram. So here's the house. I don't know why when I draw houses, they always look surprised. Like they look like surprised faces, but maybe I'll give it an awning or something. Now it just looks like a surprise face with a hat, whatever. So we have the ladder against the side of the house, and the base is 6 feet from the house. And our question is, how far up the side of the house does the ladder reach? Well, we can see that we can model this with a triangle. The ladder, we're presuming, stays straight. Oh, and the ladder is 18 feet. Hopefully my house makes a 90-degree angle with the ground. Otherwise, we might be living in the Leaning Tower of Pisa or something. So we'll kind of presume that the wall of the house is 90 degrees relative to the ground. Even if it's, a couple of degrees off, that's not going to change your answer very much. So that's probably a safe assumption to make. The bottom leg is going to be 6. That's the 6 feet where the base of the ladder over here is away from the house. And the 18 feet, the hypotenuse, is the length of the ladder. And here I have H, the height that this 18-foot ladder will reach up the side of the house. It's not going to reach 18 feet, right? If it was flat against the side of the house, it would reach 18 feet up, but I wouldn't be able to climb it because then it would just fall backwards. So I need to lean it towards the house. That reduces its height a little bit. I expect this height to be a bit less than 18. So it should be less than 18, but only by a bit, right? It shouldn't be like 10 feet or something. Clearly, it shouldn't be 10 feet because 10 plus 6, that's actually less than the height of the ladder, right? That's less than the sum of these two sides would be less than the length of the hypotenuse, and that would make a triangle. So for instance, we know that H certainly needs to be bigger than 12, but it probably should be a decent bit bigger than 12. But my Pythagorean theorem says that H squared plus 6 squared equals 18 squared, or H squared, I'll just subtract 6 squared, or 36, from both sides, is 18 squared minus 36. Let me jump back over to my calculator. redo my windows here. So I need to do 18 squared. I'll just make use of this x squared button, minus 36. That gives me 288. And then I just take the square root of that. I do second my x squared button to give a square root symbol. Not 100, 288. So square root of 288 gives me 16.97. And we want to round to one decimal place. So that's going to, the 7 is going to round the 9 up, but that rounds the 16 up. So H is approximately that. H is approximately 17.0 feet. So as we expected, H is less than 18, certainly bigger than 12, but only less than 18 by a little bit, right? If I just imagine an 18-foot ladder, like basically the height of a two-story house, kick the base out 6 feet, just from our experience doing stuff in the real world, we know that kicking that base out 6 feet, or about the length of a person, isn't going to really reduce the height of that ladder by all that much. So this both is plausible, both in the kind of mathematical side of things where we figured out what are the hard bounds on H, has to be less than 18 because it's a leg and not a hypotenuse, has to be bigger than 12 for this to be a valid triangle. So those are kind of like hard bounds. But also just kind of our like gut feeling, we said, you know, it should be less than 18, but only by a little bit. It's only a foot less, so that makes sense. Note that kicking the base out 6 feet does not like reduce the height that the ladder reaches by 6 feet. So be a little bit careful there. Right? Pythagorean theorem is what comes into play here. It's not the perimeter. Okay. So we have the relationship between these three sides. They're related by the Pythagorean theorem. We don't have some kind of constraint on the perimeter. Since we only have 5 minutes left, I don't think we have time to work through these two exercises or even one of them. So we'll punt these to next week. When we come back next week, we'll take a look at these two exercises. That'll be maybe the first thing we do. We might go through a really quick review and then look at these two and then continue on. So if you want to, you can screen cap or write down these two exercises if you want to work on them in the meantime over the weekend for a little bit of practice and be ahead of the game on Tuesday. Or if you want to wait till Tuesday, that's perfectly fine also. Let me stop my share and stop the recording. Where is my, there we go.